We're going to work through this problem of production of methyl chloride. This is going to be the end product that we desire coming out of the reactor. And this separation, you have a condenser, an absorber, a distillation column, the reactor, and then also recycle. Okay, so in producing this, let's just go to our Word version of this, and we're going to use this to develop some equations, do a degree of freedom analysis, and then solve for the different molar flow rates throughout this process. Okay, so I'm just going to go to the story problem here, just read through it briefly. Methane is going to react with chlorine. Okay, so let's go ahead and just write this reaction. So CH4 plus chlorine to produce, and this is going to produce methyl chloride, okay, plus HCl, hydrogen chloride. Okay, so once formed, the methyl chloride may undergo further chlorination to form methylene chloride. Okay, so it's going to form this methylene chloride with 2 Cl's, and in this case, it's just going to be this species here that's going to react further with the chlorine. Okay, and then we're also going to get chloroform and then carbon tetrachloride as well. Okay, so it's going to continue to chlorinate this. So let me go ahead and write these different reactions here. Okay, and the fourth one is for the carbon tetrachloride. Put a 3 here. Okay, plus Cl2 plus, okay, let me get this straight here. Okay, so here it is. We have carbon tetrachloride plus HCl. Okay, so all of these happen in this reactor. Okay, so the methyl chloride production. Okay, so this one process consists of a reactor, a condenser, a distillation column, and an absorption column. Okay, as we had on our diagram, a gas stream containing 80 mole% methane and the rest chlorine, so 20% chlorine, is fed to the reactor. Okay, so let's go over to our diagram then. Here we have this 80% and 20%. And in this case, we're just going to assume a basis of 100 moles per hour coming into the reactor. Okay, so that's just one additional piece of information that we need to specify. We're going to scale up this reactor to actual conditions later. Okay, so let's go back here to the description. In the reactor, a single pass chlorine conversion is essentially 100%. Okay, so all of it's going to be converted. The mole ratio of methyl chloride to methylene chloride is 5:1. Okay, so let's just go ahead and start writing some of this in. So this is the ratio between the two. Okay, so I just made a new variable N5. That's a molar flow rate of methylene chloride, and then the methyl chloride is going to be 5 times that. So here's I have 5 N5 and then N5 for those two. Okay, and then we have product HCl, and then possibly some unreacted methane gas as well. Okay, so that gives us N3, N4, and N5 variables. Okay, so there's negligible amounts of chloroform and carbon tetrachloride. Okay, so negligible amounts of these last two are formed. And the product stream flows to the condenser. Okay, so here's my condenser. And 2 streams emerge from the condenser. The liquid condensate, which contains essentially all of the methyl chloride and methylene chloride. Okay, so all of these, that one is just going to come down. Okay, and these two, these are going to continue forward. Okay, from the condenser. So these are going to continue as gas, and this is going to be the liquid, and there's my gas stream. Okay, okay, so let's keep going. A gas contains the methane and hydrogen chloride. The condensate goes to the distillation column, in which 2 component species are separated. The gas leaving the condenser flows to the absorption column, where it contacts an aqueous solution. Okay, so that's right here. Here's our aqueous solution, and then all of the hydrogen chloride is going to come out in the aqueous solution, and then all of the methane is going to come overhead into the recycle. Okay, so that's going to go back to the reactor. Okay, so let's see. The liquid leaving the absorber is pumped elsewhere in the plant for further processing. So at that point, the HCl is gone, and the methane is recycled to join the fresh feed to the process. Okay, that's our mixture of methane and chlorine, and the combined stream is fed to the reactor. Okay, so we have all of our information now. We chose a quantity, okay, going into the reactor feed. Okay, so that is our basis. That's our basis, and we'll draw this flow chart. We'll do a degree of freedom analysis for the overall process in each single unit and stream mixing point. Okay, then we'll write in order the equations we'd use to calculate the molar flow rate and the molar composition of the fresh feed, the rate at which the HCl must be removed in the absorber, and the methyl chloride production rate. So basically we want to be able to calculate all of the molar flow rates throughout this whole system. But what we need to do first of all is just start with a degree of freedom analysis. What the degree of freedom analysis will tell us is where we can start closing these species balances, where we can do the calculations. Okay, so we're going to start first of all just with the block. Okay, so block means what we're going to do is we're just going to put a mole balance around the whole system. Okay, and anything entering or leaving that entire system we'll analyze. Okay, now in this case we're going to be doing degree of freedom analysis a little bit differently if it's reacting or not reacting. Okay, so if it's reacting, we're going to do an elemental balance. And if it's not reacting, we'll do a molecule balance instead. Okay, so first of all, for the block, let's go ahead and just do this calculation for the block. I'm going to go ahead and zoom in here. And what we'll do for each of these is we will calculate, or we'll tell how many unknowns we have, how many elemental balances we have if it's reacting, how many non-reacting species are involved, and then other equations as well. Okay, so in this case, the unknowns around the block, okay, so we only have N5 coming out, N4 coming out here, and then N1 and N2. Okay, so in that case, we're going to have 4 unknowns for this. Okay, so let's count up the number of elements that we have. We have carbon, we have hydrogen, and we have chlorine in each of these species. And that's it. Okay, so that's going to be 3. Okay, and so we're going to take away, we can do 3 element balances. We have no non-reacting species and no other equations. So degrees of freedom for this are going to be 1. Okay, so we don't have enough information to solve this one. Let's go with the mixing point. Okay, so that's going to be right here, our mixing point. Okay, where those streams are going to combine. And so so this is not reacting, it's just mixing different species together. So let's go ahead and do a species balance, okay, not the elemental balance. In this case, we're going to have unknowns. We're going to have N1, N2, and N3. Okay, so those are our 3 unknowns. And then number of species that we have is going to be 2. Okay, so we just have methane and the chlorine, both of them gas there. Okay. Okay, so species 2, and then other equations, we don't have any of those. So again, we have 1 degree of freedom. So it's still not solvable. So let's do it around the reactor now. Now the reactor, this is reacting. Okay, so we're going to do the elemental balances. So unknowns, we have N3, N4, and N5 around the reactor. Okay, so that's going to give us 3 unknowns. And then elemental balances, again, we have the carbon, hydrogen, and chlorine. That's going to give us 3. Okay, and then other equations or non-reacting species, we don't have any of those, so that's going to give us 0 degrees of freedom. That means we can solve this with the available information that's there. Okay, Okay, let's just continue with our condenser. Okay, this is going to be non-reacting. Okay, we have unknowns here. We're going to have N3, N4, and N5. Those are our unknowns around the condenser. And then our species balances, we actually don't have any species balances that we can write. Okay, we just knew that it basically split into two. All of this comes down here, and all of these top two come over. Okay, so we have really no balances. It's just trivial. The N3 coming in is equal to this N3 going out. If you did want to write a species balance, you would need to create a new degree of freedom. So let's make this N6, and then just say N6 equals N3. Okay, so pretty trivial. So that's why we eliminate the species balances for this condenser. So we have three unknowns. We have no balance equations that we can write. Okay, so these are our species balances. And then other equations are 0 as well. Okay, so we actually have 2 degrees of freedom here for the condenser. Okay, so so this was not reacting. So I'll just circle the ones that are reacting. Okay, so reactor, and then we also had for the block, and so that's why we did the elemental balances. But for the other ones, we did a species balance. So let's just look at the absorption column now. Okay, so here's our absorber. Okay, it goes to the aqueous solution, and the HCl basically gets absorbed out and put into a liquid stream that is processed elsewhere in the plant. Okay, so in this case, we have unknowns. We're going to have N3 and N4. And then species balances, again, we don't have any, okay, because you would have to rename this N4, for example. That would be like N6, and then N6 equals the N4 coming in. Okay, and again, trivial, we can just eliminate that and say we have no species balances because we named this N4 and we named that N3, just to eliminate those equations. Okay, so we have no species balances that we can, no additional information that we can use to reduce degrees of freedom, and so that's, and no other equations there as well. 2 degrees of freedom for the absorption column. Okay, so let's go to the distillation column now. Okay, so in the distillation column, we really only have one variable right here, which is N5. Okay, there's our distillation column. Now, let's see, species balances, how many we have. Okay, again, it's going to be 0, and then other equations are going to be 0. So 1 degree of freedom around the distillation column. Okay, so what is the strategy then for solving this? One approach is to just take a look at the degrees of freedom, and here we see that our reactor actually had 0 total degrees of freedom. So we can actually start here if we want to. So let's just start with the reactor, and so our solution strategy is to just start writing the element balances. And we had a basis of 100 moles per hour. Okay, and then times 80% of that is going to be the methane gas, and then 20% of it's going to be the chlorine gas. Okay, so let's just write a carbon balance. Okay, so what's coming into the reactor is going to be just the 80 moles of CH4, which equals 80 moles of carbon coming in. Okay, and that's going to be equal to, okay, let's look at the moles of carbon coming out in our product stream. So that's going to be N3, and then let's see, we have plus 5N5 plus N5. Okay, so we've written our carbon balance. Okay, so now let's write a balance. Let's see, let's go ahead and write it for the hydrogen now. And so we know that we have 4 times the number for our basis, okay, times 0.8. Okay, so that's going to be our hydrogen coming in. That's just the methane here. We have 4 hydrogen atoms for every methane. And so coming out, okay, so this is going to be 4 times N3. Okay, again, that's our methane coming out. And then we're going to have one from our N4. Okay, so that's a HCl. So one hydrogen, and then plus, and then so we have 15 times N5. Okay, so we had 5 N5 coming out. Okay, and then there were 3 hydrogens for every of these methyl chlorides. Okay, so that's going to be 15 N5, and then plus, and then that's going to be 2 times N5. Okay, so we had 2 more coming out with the methylene chloride. Okay, so now let's do another one. Let's do it on the chlorine as well. Okay, so there's none of these that just have one variable. If we did, we'd just solve that one first of all. But let's go ahead and go with our chlorine now. Okay, so that's going to be 2 times the basis number. Okay, now this is going to be times 20% of that basis is going to be the HCl. Okay, so or the Cl2, the chlorine gas. Okay, and then we have 1 coming out with the N4. Okay, that's our HCl coming out, and then plus 5 N5 plus 2 N5. Okay, so that's a chlorine balance. So here we have, if we say that our basis was 100, let's just say that's going to be 100 moles per hour. Then here we have 3 equations, 3 or 4, you could say 4 if you included this as, and then 3 unknowns. Okay, so we just have N3, N4, and N5, and we had these 3 equations, 3 unknowns. Okay, so we can solve this now, and let's go back to our problem description. It said don't do no calculations in this part. So for the next part, let's go ahead and calculate the quantity specified in part A, either manually or with an equation solving program. Okay, so you can do this in Excel, you can do this in MathCAD, and there's a lot of different equation solving programs that can solve 3 equations, 3 unknowns. It's not a particularly challenging problem to do. So we're just going to do this through a web interface. I'm just going to come to, in this case, the APMonitor.com website. Okay, so if you come to APMonitor.com and then go to solve optimization problems. Okay, and I'm just going to go ahead and put my problem right here in this window. Okay, so go ahead and erase that if you'd like to follow along. And what we'll do is we'll just put in those equations from our 3 equations, 3 unknowns, and put those in here and then solve it. Okay, just to see what answer it gives us. Okay, so I'm going to come over here and just create some variables. Okay, let me make this just a little bit bigger so it's easy to see. Okay, so we'll create a new variable section, and I'll just say I have N3, N4, and N5. Okay, for my variables, and then equations, I'm going to have 80 equals N3 plus 5 times N5 plus N5. Okay, and the next equation is going to be 4 times 80 equals 4 times N3 plus N4 plus 15 times N5 plus 2 times N5. Okay, I could have done 17 times N5 there. Okay, and then 2 times 20 equals N4 plus N5 times N5 plus 2 times N5. Okay, so I have variables and equations there, and then I'm going to just go ahead and select this green button, okay, which is going to solve it right here. And when I select that, it says that there was a successful solution, and then gave me the answer for my N3, N4, and N5. And you can click here to view solution results if you want in a tabular format. Okay, so there's N3, N4, and N5 values. Okay, but if you remember, we had a couple additional equations or variables, we also wanted to find N1 and N2 as well. So in order to do that, let's just do our mixing. Okay, so we had 1 degree of freedom before, but now we know N3. And so this will tell us if we do the species balances around our mixer, then we'll get N1 and N2 as well. Okay, so I'm just going to come down here and do the N1 plus N3 equals 80. Okay, and then N2, this is for the this is just going to be for the chlorine gas. Okay, N2 equals 20. Okay, because N2 was equal to 20 right here, and we had no N2 coming back from our recycle. Okay, the N2 or the chlorine gas coming back was 0. Okay, so N2 was equal to 20, and then N1 plus N3 was going to be equal to this 80. Okay, so I can put those into my equation solver as well if I wanted to. Okay, so let me go back there and just say that, okay, come back here and just create 2 new variables. Okay, and just say that N1 and N2 are going to be new variables, and we'll have 2 more equations. Okay, we can just solve all of these simultaneously. It's also easy just to rearrange those and solve them. We're just going to show you this numerically. Okay, and then when I solve it, okay, if I come down, then it's going to also have the N1 and N2 values. Okay, so I'm going to come back here. Let's just answer this very last one now. This last one is if we want to if we want to be able to produce 1,000 kilograms per hour, okay, of our product, how much am I going to need? What's my basis got to be? Okay, so if I just switch back here, okay, so now instead of equal to 80, I'm just going to create a new variable, which is my basis times 0.8. Okay, and then basis times 0.8, and then this was my basis times 0.2. Okay, so I put in a new variable, which is my basis. Okay, and now N5, we want that to be, okay, 5 times N5 has got to be equal to, let me just make a new equation now. Okay, so 5 times N5 has got to be 1,000 kilograms per hour. But we're going to need to, let's see, so kilograms per hour, we need to put this in terms of moles though, because N5 is in terms of moles. So if we have kilograms, the way that we'll convert that to moles is divide by the molecular weight. Okay, so let me do that for the methyl chloride, and that's going to be divided by 50.5. Okay, so we just put one more variable and one more equation down here. And so let's just go ahead and solve this. Okay, so successful solution. Oh, I think I made a mistake here. Let's see, 5 times N5. Let me see if I can go back to my problem. Okay, so coming out, 5 times N5 has got to be 1,000 kilograms per hour. Okay, so I'm going to go back to the equations. Okay, oh, there it is. Okay, so these also need to be converted to the basis times 0.8, and then the basis times 0.2. Okay, so I just had to make sure I replaced all of those with these new variables, and then if I solve it, then I can see there's my basis. That's going to be in kilomoles or kilogram moles per hour. So before I had a basis of 100 gram moles per hour, so it's quite a bit more, about 1,000 times more than we had originally assumed for our basis to be able to get that production flow rate. Okay, so that concludes this example. What we did, let me just summarize that. We took a story problem, and what we did is we then mapped out all the different units. We did degree of freedom analysis. If it was reacting, we did an element balance for the element balances for the degree of freedom analysis. And then we saw that the reactor had 0 degrees of freedom. Okay, and so from there we started with the reactor, set up our balances, and then added 2 more for N1 and N2. And then as a final step, we said, well, we assumed a basis, but really what we want to do is we want to produce a certain amount in the end. And so we just changed our equations, added a new variable for our basis, and then also another equation that would specify how much is coming out of the reactor. Okay, so this is just the tutorial on producing methyl chloride degree of freedom analysis with reacting systems.